Okay, so we're going to cover troubleshooting parallel circuits. So let's start by examining this first circuit. Okay. Now we have a voltmeter displaying 0 volts basically. Okay. And then we have our leads. The negative lead is always here. You can't move the negative lead. And so the point of these exercises is to troubleshoot this parallel circuit and determine what is not working. Now you have several options here. Basically you have one of these wire traces is open, or you have a resistor is blown, or there is nothing wrong. Okay? And so when I mean resistor is blown, that one of either R1, R2, or R3 is blown open. Okay. Now a trace is a solder trace that goes onto a circuit board, and basically that's a wire. So we're trying to troubleshoot which one of these thin laminate pieces of wire on a circuit board is not working. Okay. So examining what we have right now on this first trace, I see that I'm reading 0 volts. There is no difference in potential between on trace 6, which is what you should read if the wire or the trace is good, because even though current or voltage is flowing on our power supply right here, it's displaying our voltage, and it's displaying the total current of the circuit right now. If I touch the same wire, there's actually no difference in potential, and I will not get a reading. So I'm going to move my meter over here. I still have 0 volts. Trace 5 is good. Here I still have trace 4, 0 volts. It's still good. Let's come over to trace 3. So that tells me that this bottom part of the circuit, this wire right here, all the way over here, is good. I don't have to worry about it anymore. So let's move up to the top part of the circuit. Let's start over here on trace 2. And let's go ahead, we'll have to trash that in the way. So we're going to check over here at trace 2. So now I'm actually reading voltage because there is a difference in potential across the resistors. Okay. And so it's telling me that I have voltage here. If I wanted to, I could continue on and trace out the next one, etc., etc. But since I'm reading it all the way at the end of trace 2, I know that the rest have to be good, because current is flowing here all the way through here, and I know that it is good because it's actually making it all the way down here and displaying 19 volts here. And my power supply says I have 19 volts. So, what do I do now? I don't have a broken wire. Well, in this instance, we have to determine which one of these resistors is blown. Okay? And to do that, we're going to have to do some calculations. So the first thing we need to do is determine what R1 and R2 and R3 are. And to do that, I have to look at the resistor color code. Now I'm going to tell you so far on this exercise that this is not orange. It is not displaying an orange band. That is actually a red band right there. And so I have not seen an orange band because they're going to look very similar. So if I look at my color code chart, I will see that R1 equals 270 ohms. All right. R2, using the color code, equals 560 ohms. All right. And then R3, using the color code, equals 1200 ohms. Okay. So now that I have those values, I'm going to erase this off up here. I can do some calculations to determine which one of these resistors is blown up, or what if none. Okay. Well, let's go ahead and calculate what our current should be, okay? Because I can calculate what the current should be. And I could do that simply two ways. I could calculate the individual current draw across each one and add it up. All right, or I could calculate total resistance and see what total current should be. So let's go with total resistance. Formula for total resistance is going to be RT equals 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. If I had another resistor, I would simply put R4, so forth and so on. All right. And so when I do those calculations, I determine, first of all, I will take the reciprocal of 270 ohms. And I end up with R1 equals 3.7 milliamps. Okay. Oh, I'm sorry, not milliamps, but that's just this first part over here. Erase that. So I reduce it down, and I see that I'm actually getting 0.0037, et cetera, et cetera. So I'm going to go ahead and take 0.0037. I'm going to take the reciprocal of R2, which is 1 over 560. All right. Which I'm not carrying all of these places all the way out, so you probably want to carry them out a little bit further than I do. I'm actually punching numbers into the calculator. So 178, all right? And so that's the reciprocal of 1 over 560 ohms. And so I'm going to go to the next one over here, and I'm going to add the next one. Of 1200 ohms. And I'm going to use the inverse function on my calculator. And that one is 0.00083. All right. And so when I add all of those up, I get a big long number of 0.00632, et cetera, et cetera. And so now I'm going to take that final number that I've gotten and take the inverse of it, and I come up with 158 ohms. All right? And so that is my RT. So now my RT equals 158 ohms. Now, if I want to solve what my total current should be, I simply use Ohm's Law, and I can take my voltage, which is 19.07, come down here, and we'll take 19.07 volts, VT. Remember, in a parallel circuit, our voltage is the constant, and every chance I get, I want to use my voltage for these calculations using Ohm's Law. So 19.07 divided by RT, which is 158 ohms. RT. All right. And so I'm going to divide by 19.07 divided by 158 ohms, which gives me a total milliamp draw of basically 120.6 milliamps. So that is going to be my IT right here, IT. All right, so IT is 120.6 milliamps. Okay, well, if I look at my power supply, I see I'm actually drawing 49.97. So that's going to tell me right now that one of these resistors is bad. I don't know which one. The only way to figure that out is to calculate the individual current draw across each one of these resistors using Ohm's law. To do that, we're going to use the same formula. We're going to use our constant of 19.07. So instead of using RT, I'm going to use the individual resistors. So I'm going to go with 19.07 divided by R1, which is 270 ohms. So it's 19.07 divided by 270 ohms equals about 70.6 milliamps. 70.6 milliamps. All right. So then I'm going to move on to the next one. And we're going to do R2, which is 19.07 divided by 560 ohms. Which gives me a milliamp reading of basically 34 milliamps. Equals 34 milliamps. All right, moving on to the last one. I see that I'm going to use 19.07, and that's going to be divided by R3, which is 1200 ohms. So 19.07 divided by 1200 ohms gives me a milliamp reading of 15.9 equals 15.9 milliamps. All right. So now I have 70.6, 34, and 15.9 milliamps. If I were to add all of those up, they should equal my total milliamp, which is 120.6. So I can check my math, make sure I did everything correctly. So I'll take 70.6 plus 34 plus 15.9, and that gives me basically 120.5. Well, I didn't carry my decimal points all the way, but pretty close, and so I would say that my calculations are correct. So we are showing 49.97 milliamps on our power supply, right up here. Right here, all right? So what number of current draw across each resistor equals our current that we are showing on our power supply? Well, let's see. What is 34 milliamps, which is R2, plus 15.9, which is R3, gives me 49.9 milliamps. So IR2 plus IR3 equals 49.9 milliamps. And that is what I'm displaying on my power supply right here. So that tells me that R3 and R2 are good. They're fine. But R1 is not being added into that. So that tells me that R1 is blown open, that there is no current flowing through that one. That even though it's there, it might as well be an open wire. Okay. So I'm going to come over here and I'm going to select R1 open. All right. And then I'm going to grade by item, and I got it correct. Great. All right. So that carries on to our next one. And we've seen how to calculate the resistors, so I might skip through some of these because I want to show you how to calculate using your meter and just tracing the voltage. Okay, so I'm going to kind of clear some of this off because our values have changed. Take this off. We can leave the resistor formula on there. Get all of this out of the way because we have another circuit. However, our resistance values have remained the same. Okay, they are 270, 560, and 1200 ohms. So let's check it with our meter. It's showing 0 volts, which is okay. That's correct. I'm going to move my red lead over here. I'm still showing 0 volts. Still showing 0 volts. Still showing 0 volts here. So I'm going to start back over here. What am I showing? 0 volts. Well, if this was connected all the way over here in our previous example, I should be reading 11.15 volts, and I'm not. So let's move on one more. So I'm going to come over here, and I'm going to move over to trace the middle between trace 1 and 2. So if I have voltage there, and I have no voltage here, well, I thought I, yep, voltage here, and I'm reading 0 volts there because I should be reading 12 volts right there. That tells me that trace 2 is open. So I'll select trace 2, and I will grade the out. Hit continue. All right. And so here we are. Let's try another one. Here we're still reading 0 volts, which is correct. There should be no difference of potential. I come across here. Everything's good. Now I'm going to come over here to trace 2. I'm reading voltage. I don't need to go any further because now I'm showing 29 volts at this point that this entire circuit is gone. Good. So now what do I have to do? I have to calculate my total RT, just like we did earlier, or I can calculate the individual voltage drops across, or individual current drops across each resistor and determine whether this milliamp reading is correct or incorrect. If it is correct, then I have no fault. So I'm going to end the video right here because we've already calculated this once, but first thing you're going to have to do is look on your color code and determine the values of the resistor and follow the first part of the video.